OCR Chemistry A 5.2.1 Lattice Enthalpy. Using Chemistry Explained needs your active participation. You need to write notes and complete the tasks either with pen on paper or on a tablet. Control the pace of the lesson by pausing or replaying the slides. Most important, when prompted, pause the lesson, complete the task, thinking the problem through, which means taking your time. When you're ready, continue the lesson, correcting your work. So we'll start with a generalized idea of lattice enthalpy, look at calculations using Born-Haber cycles, trends in lattice enthalpy data. Then we'll look at enthalpy change of solution and factors which affect enthalpy change of solution and enthalpy change of hydration. So let's think about the general idea of lattice enthalpy, which is or can be thought of as a measure of the strength of ionic bonding within a giant ionic lattice. So a quick review of year 12 chemistry here. In an ionic compound, we have positive ions surrounded by negative ions in all directions. And similarly, each negative ion is surrounded by positive ions in all directions. And we keep building up that pattern so that we form a giant ionic lattice. Now, electrostatic attractions form between the oppositely charged ions, but a point that wasn't made in year 12 most probably is that, of course, the positive ions are attracted to the negative ions, but the positive ions are also attracted to the negative ions that are at a greater distance. So both the immediately surrounding ions and the more distant ions, if they're oppositely charged, they will form attractions. Similarly, the positive ions will form repulsions with the other positive ions. So we have an overall strength of bonding, which is the difference between the electrostatic attractions and the electrostatic repulsions between same charged ions in the whole lattice. As with all enthalpy changes, there is a definition that must be known. The lattice enthalpy is the enthalpy change on forming, in OCR Chemistry A, it is defined by forming 1 mole of ionic lattice from the gaseous ions at standard conditions. If that is the definition, write an equation which expresses the idea of the lattice enthalpy for sodium chloride. Pause, write the correct equation, come back to check. Okay, so if I reveal the equation, we're forming 1 mole of sodium chloride from the necessary ions in the gaseous state. The value of the lattice enthalpy for sodium chloride is minus 780 kilojoules per mole. It is a molar quantity. So, write the equation that expresses the idea of the lattice enthalpy of magnesium chloride. Pause, write the equation, check when you're ready. Okay, so I'm going to reveal 1 mole of magnesium chloride from the required ions, magnesium 2+ and 2 chloride ions in the gaseous state. The lattice enthalpy of magnesium chloride is minus 2526. You'll notice that for a definition which has enthalpy change on forming 1 mole of ionic lattice, lattice enthalpies are always exothermic. So to carry out calculations of lattice enthalpy, we're going to construct Born-Haber cycles, which is simply an application of Hess's law, that is, enthalpy change is independent of the reaction pathway, to ionic lattice formation. Now you will remember Hess's law being applied to covalent molecules in year 12. We're now going to apply Hess's law to the formation of ionic lattices. But we must, as always, be very consistent in our use of enthalpy change definitions. The enthalpy change of formation will have been met in the context of covalent bonding. Could you write a definition of the enthalpy change of formation? Pause, write your definition. Okay, now you may need to correct it, but I hope you've had a go. It's the enthalpy change on forming 1 mole of compound from its elements at standard conditions. So could you write an equation that expresses the idea of the enthalpy change of formation for sodium chloride? Pause, write the equation. Okay, so I'm now going to reveal. We are forming 1 mole of compound, so sodium chloride, from its elements. Sodium at standard conditions is a solid, and we need half a mole of chlorine gas, Cl2. You will also recall that you've met first ionization energies. Could you define first ionization energy? Pause, then come back to correct. Okay, so I'm going to reveal. So the enthalpy change on forming 1 mole of unipositive 1+ ions from the atoms in the gaseous state. If that is the case, can you write an equation to express the first ionization energy of sodium? I'm about to reveal. Check your equation against this. We're forming 1 mole of 1+ ions from the atoms in the gaseous state. So we need some other enthalpy change definitions, which you will have met before. Second ionization energy. Could you write the definition for the second ionization energy? Pause and come back. Okay, so to reveal, the second ionization energy is the enthalpy change on forming 1 mole of 2+ ions from 1+ ions in the gaseous state. So could you write an equation to express the second ionization energy of sodium? Pause, come back to check. Okay, so revealing, we're forming 1 mole of 2+ ions from gaseous 1+ ions. You'll notice we're balancing, I forgot to mention on the previous slide, we're balancing for charge with the electron that has been lost. So 1 mole of sodium 1+ ions forms 1 mole of sodium 2+ ions with the loss of 1 mole of electrons, all in the gaseous state. Have you met the enthalpy of atomization? If you have, try and recall. If you haven't, come up with a definition for the enthalpy of atomization. Pause, try it, then correct. Okay, so to reveal, the enthalpy of atomization is the enthalpy change on forming 1 mole of gaseous atoms from the element in its standard state. So if that is the definition, can you write an equation to express the enthalpy of atomization for chlorine? Pause, write the equation. Okay, to reveal, we're forming 1 mole of gaseous atoms. So these are not molecules, these are gaseous atoms. 1 mole of gaseous atoms from the element in its standard state or at standard conditions. So chlorine, Cl2, we only need half a mole because we're only forming 1 mole of gaseous atoms. So it's half a mole of Cl2 molecules in the gaseous state, of course. Okay, so we're going to move on to enthalpy change definition, which you probably haven't met before, which is the idea of electron affinity. So we have first electron affinity. I'm going to define it for you. Is the enthalpy change on forming 1 mole of 1 negative ions from atoms in the gaseous state. So it mirrors the first ionization energy, except we're forming 1 negative ions from the atoms in the gaseous state. If that is the case, can you write an equation to express the idea of the first electron affinity for chlorine? Pause, write that equation. Okay, so to reveal, we're forming 1 mole of chloride ions in the gaseous state. So we start with chlorine atoms, 1 mole, gaining 1 mole of electrons to form 1 mole of gaseous chlorine 1 minus ions. So if that's the definition for first electron affinity, I think it would be fair to ask you to write a definition for the second electron affinity. Pause and write that definition. Okay, so to reveal, it's the enthalpy change on forming 1 mole of 2 minus ions from the 1 minus ions in the gaseous state. So could you write an equation to express the idea of the second electron affinity for oxygen? Okay, so I hope you've written an equation. I'm going to reveal the correct answer. We're forming 1 mole of 2 minus ions in the gaseous state from 1 minus ions, oxygen 1 minus ions, by the gain of 1 mole of electrons. So 1 mole of 1 negative ions gains 1 mole of electrons to form 1 mole of 2 minus ions. We're now going to move on to calculating lattice enthalpy using Born-Haber cycles, which is dependent on the correct use of the enthalpy change definitions we have just reviewed. So let's construct a thermochemical cycle which allows us to calculate lattice enthalpy. So I've put out a sort of a framework. I'm going to put in some changes which we then need to define. So the first change I put in is sodium and chlorine going to form 1 mole of sodium chloride. Pause and identify that enthalpy change. Okay, so if I reveal, that enthalpy change is the enthalpy of formation for sodium chloride. 1 mole of sodium chloride from the elements at standard conditions. Now, what I'm going to do is equate that enthalpy change to all of the enthalpy changes in an alternative route from sodium and chlorine to sodium chloride. So we're going to apply Hess's law and say that this route going from sodium and chlorine directly to 1 mole of sodium chloride will be equal to all of these changes, which I will add the detail for, added together. That is our basis of applying Hess's law, that is a Born-Haber cycle. So let's look at some of the changes that are necessary. Well, we need to turn sodium into gaseous sodium atoms. Pause and identify that enthalpy change. Okay, so that is the enthalpy of atomization of sodium. Identify the enthalpy change where we take half a mole of chlorine molecules to form 1 mole of chlorine atoms in the gaseous state. So to reveal, that is the enthalpy of atomization of chlorine. I'm now going to transform or change gaseous sodium atoms into 1 mole of sodium 1+ ions. That, of course, is the first ionization energy for sodium. And my next stage would be to turn chlorine atoms into 1 mole of chloride ions. Pause and identify that enthalpy change. Well, to reveal, that enthalpy change is, of course, the first electron affinity for chlorine, and then forming 1 mole of sodium chloride from its gaseous, free and gaseous ions is, of course, the lattice enthalpy for sodium chloride. Now, just one side issue is, or point to note, is that as this is enthalpy on the y-axis, an upward arrow is an endothermic change, whereas a downward arrow indicates an exothermic change. And as we saw earlier, all lattice enthalpies are exothermic, hence they all have a downward pointing arrow. Now, we can now use Hess's law to equate this green pathway to A plus B plus C plus D plus E. So the grey pathway must be equal to the green pathway. So delta HF, the enthalpy change of formation, is A plus B plus C plus D plus E. So that would be applying Hess's law to ionic lattice formation, that is the construction of a Born-Haber cycle. So we're now going to try and use it to solve a problem. So we can now use Born-Haber cycle to solve a problem, such as what is the value of the lattice enthalpy of sodium chloride? Obviously we need some data to work with. So we've got the enthalpy of atomization for sodium and for chlorine. We've got the first ionization energy of sodium, the first electron affinity for chlorine, and the enthalpy of formation for sodium chloride. So that data can be used to calculate the lattice enthalpy for sodium chloride. Pause, attempt that calculation, come back to check. So we're going to use Hess's law. We're going to say delta HF is equal to all of the other changes added together, which I've labelled A, B, C, D as per the previous slide, and just identified the lattice enthalpy as the unknown that we need to focus on. If we put in all of these numbers and rearrange, we will find, or solve for lattice enthalpy, we'll find it comes to minus 788 kilojoules per mole. So I'd like you to now attempt this problem. Construct a Born-Haber cycle for magnesium chloride. A template or a framework is set out for you there. Not all of that is necessary and to be used. And then use that framework to calculate the enthalpy of formation. Notice the enthalpy of formation for magnesium chloride. The data you're supplied with is enthalpy of atomization of magnesium and of chlorine, first and second ionization energies for magnesium, first electron affinity for chlorine, and the lattice enthalpy for magnesium chloride. So construct a Born-Haber cycle, That is, put in all the relevant particles, make sure everything is balanced at each point in the Born-Haber cycle, then use that cycle to solve for the enthalpy of formation for magnesium chloride. Pause, take your time, work your way to a solution, and then come back to check your answer. Okay, so I am about to reveal the Born-Haber cycle. We've first of all got to atomize magnesium and then atomize chlorine, but notice we're making 2 moles of chlorine atoms because we need here 2 moles of chloride ions, so we need 2 moles of chlorine atoms. So this is the enthalpy of atomization of chlorine times 2. Enthalpy of atomization is a molar figure. We're forming magnesium 1+ ion, that's the first ionization energy of magnesium, and then we're forming 1 mole of magnesium 2+ ions from the 1+ ion, that's the second ionization of energy of magnesium. We're then, on this part, obviously we're balancing up with Mg2+ and 2 electrons. Those electrons are transferred to the chlorine atoms to make 2 moles of chloride ions, so that's the electron affinity of chlorine times 2, and then the lattice enthalpy of magnesium chloride, for which we are given the value. So we simply equate delta HF to all of these values summed together, making sure we've multiplied the enthalpy of atomization of chlorine by 2, used the first and the second ionization energies of magnesium, and then multiplied the first electron affinity of chlorine by 2. So delta HF will equal all of these other enthalpy changes added together. And we get an answer as we see. If you have access to the endorsed OCR textbook, I would suggest at this moment that you look at the summary questions 1, 2 and 3 on page 351 and then check your answers against those on page 578. Moving on to explaining trends in lattice enthalpy data. So let's start with trends in ionization energies, and this reviews some work from year 12. Let's look at first ionization energy for sodium at +496 and for magnesium at +738. Pause and either write down or speak out an explanation for that ionization energy difference or ionization energy trend. Come back to see my explanation when you're ready. Okay, so I'm going to reveal my explanation is that sodium has 11 protons in its nucleus, whereas magnesium has 12 protons, and therefore magnesium nucleus forms stronger attractions for the outer shell electrons than the sodium nucleus does for the sodium outer shell electrons. Bearing in mind that the distance between the nucleus and the outer shell and the inner shell shielding is the same for sodium and for magnesium. So the only difference is effectively that sodium has 11 protons, magnesium has 12 protons, and therefore the electrostatic attraction for the electrons in the outer shell is stronger in magnesium. So let's look at successive ionizations. Magnesium, first ionization energy, magnesium, second ionization and ionization energy. We can see the second ionization energy is much higher than the first. Pause and come up with an explanation for that trend, please. Okay, so I'm going to reveal my reasoning. For the second ionization, you're removing a second electron or a second mole of electrons from an already positive ion. The first ionization involves removing electrons from, or an electron or a mole of electrons from a neutral atom. But to remove an electron from an already positive particle, an already positive ion, requires more energy. So let's look now at electron affinities, and of course the arguments about electron affinities where electrons are gained rather than lost is going to be opposites to those arguments for ionization energies. So the first electron affinity for chlorine is exothermic by 349, whereas for bromine, exothermic by 325. Pause. Can you come up with an explanation for that trend? Okay, so if I reveal my thinking, chlorine is smaller as an atom compared to bromine, so the nucleus is closer to the outer shell. Therefore, there are stronger attractions between the nucleus and the electron to be gained. So electron affinity is about gaining an electron, so there's stronger attractions between the nucleus and the gained electron in the outer shell of chlorine compared to that of bromine, because the chlorine atom is smaller, so the nucleus is closer to the outer shell. One can do a more detailed argument, but that is the main point. Now, what about successive electron affinities? Here we see a difference between ionization energies trends in that we have a discontinuity in that the first electron affinity always tends to be exothermic and the second, not just for oxygen, tends to be endothermic. So please pause, come up with an explanation for that trend. Okay, so I'm going to reveal my thinking. Forming a 2- ion requires both the first and second electron affinity in the Born-Haber cycle. The second electron affinity is endothermic. The first electron affinity, we're adding an electron to a neutral atom, so we're forming attractions between the nucleus and this electron, so that will be exothermic. Whilst we are forming attractions between the electron and the nucleus of the 1- ion, we've also got to overcome electron negative ion repulsions. So this electron has to overcome the negative repulsions, and therefore that requires energy, and delta H is positive. That is, the second electron affinity is endothermic, and that will always be the case. So let's look at trends in lattice enthalpies. For comparison, sodium chloride, exothermic, negative 780. Magnesium chloride, negative by 2526 kilojoules per mole. Considering the charges on the ions, pause and come up with an explanation for that trend in lattice enthalpies. Okay, so I'm going to present my thinking or argument. Keeping it simple, sodium forms a +1 ion, or 1+ ion I should say. Magnesium forms a 2+ ion. Therefore, the attractions that result between the magnesium or the cations and the chloride ions are stronger for magnesium at 2+ than for sodium at 1+. So we've got stronger attractions and therefore more exothermic lattice enthalpy. Now we also should consider ion size. If we look at sodium and rubidium, and we keep the anion the same at the chloride ion, we'll see that the sodium chloride lattice enthalpy is minus 780. It's less negative, that is, the ionic bonding is not as strong in rubidium chloride. Pause and come up with an explanation. Okay, so my explanation is that the rubidium plus ion is larger than the sodium ion. So that means that weaker attractions form between rubidium and chloride ions than between sodium and chloride ions. We can think of it in terms of the distance apart of the ions. If you've got a larger ion, then the distance apart of the ions, the average distance apart of rubidium and chloride ions, will be greater than the distance apart of sodium and chloride ions. So sodium and chloride ions will be effectively closer together and therefore form stronger attractions. You can argue that rubidium and chloride ions are further apart and therefore form weaker attractions. The rubidium ion is larger than the sodium ion. Bear in mind that the stronger the ionic attractions, that means the lattice enthalpy values will be more exothermic, that is, more negative. So the more negative the lattice enthalpy value, the stronger the ionic bonding. And that also means, of course, that if the ionic bonding is stronger, then the energy needed to separate the ions will be greater, and therefore melting points will be higher. So there's a relationship between lattice enthalpy and strength of ionic bonding and melting point. The stronger the ionic bonding, the more negative the lattice enthalpy, the higher the melting point. Moving on to the enthalpy change of solution. Enthalpy of solution, of course, has a definition. It's the enthalpy change on dissolving 1 mole of solute completely. You will see different definitions, but this is the working definition used by OCR Chemistry A. So if that is the case, can you write an equation that expresses the idea of the enthalpy of solution of sodium chloride? Pause and write your equation. Okay, so to reveal my idea, here is the solute, 1 mole. We indicate the presence of water, you will see often expressed as AQ. And then we are forming the free aqueous ions on the right-hand side. So we're producing free aqueous ions from 1 mole of the ionic solid, or the solute. Now this equation can be split, or this change can be split into 2 steps. Firstly, dissociation. So we're starting with an ionic lattice. So here's our ionic lattice. Let's turn that into free gaseous ions. So that, of course, is the opposite direction for the lattice enthalpy. So the enthalpy change for that change, the dissociation of the lattice enthalpy, of the lattice, I beg your pardon, is minus the lattice enthalpy change. And having formed the gaseous ions, well, then we can turn them into aqueous ions. So the gaseous sodium ion becomes an aqueous sodium ion, the gaseous chloride ion becomes an aqueous chloride ion, and that process is called hydration. Delta H for this will be the sum of the 2 hydration enthalpies, which is defined as the enthalpy change on dissolving 1 mole of the gaseous ion in water. So gaseous sodium ions to aqueous sodium ions, that's the enthalpy change for that is the enthalpy of hydration of the sodium ion, and then 1 mole of chloride ions to form gaseous chloride ions to form 1 mole of aqueous chloride ions. Well, that's the enthalpy of hydration for chloride ions. So the total enthalpy change, delta H, for this process, the hydration of the gaseous ions, is the sum of the hydration of the enthalpy of sodium ions and the hydration enthalpy of chloride ions. Now we can arrange the process, the solution, the dissociation and the hydration into an enthalpy cycle. So I've got a template here. I think I'll run through the process for sodium chloride. So we're starting with the solid sodium chloride, or the ionic lattice, and here we're forming the aqueous ions, and that of course is the enthalpy of solution for sodium chloride. But we can also go in an alternative route. We can go from the ionic lattice to the free gaseous ions, and then that of course is the negative of the lattice enthalpy. We can then go from the gaseous, free and gaseous ions to the aqueous chloride ion, and that of course is the hydration enthalpy of chloride ions. And then if we look here, we've got sodium gaseous to Na plus Aq. That of course is the hydration enthalpy for the sodium ion. So I'm hoping it's very clear that in the way I presented it. We're going to use Hess's law to say the enthalpy of solution is the sum of all of these enthalpy changes. But bear in mind that as I've written it, in the direction I've written it, direction of my arrow, that enthalpy change is the negative of the lattice enthalpy. At the bottom, we're forming hydrated ions, of course. So the blue route equals the gold route, as I've expressed it by Hess. So the enthalpy of solution is the negative of the lattice enthalpy of sodium chloride plus the enthalpy of hydration of the sodium ion plus the enthalpy of hydration of the chloride ion. If I give you this data, you'd like to move on and calculate the enthalpy of solution of sodium chloride. Pause and complete the calculation. Okay, so here I'm putting in the necessary steps. This of course is enthalpy of solution. This is, let's maybe write these in. So this of course, we want to work out what enthalpy of solution is, so we don't know that. We know this is minus 780. The enthalpy of hydration of the chloride ion is minus 363, and of the sodium ion minus 406. So please note it's minus a negative number. So we've got enthalpy of solution is minus 780. Minus 406 minus 363 comes to plus 111 kilojoules per mole. If I could correct my error, the answer to the previous problem was plus 11. I simply misspoke. So let's have a look at the next problem. Given this data around about the magnesium bromide ionic lattice, construct an enthalpy cycle and calculate the enthalpy of hydration of the bromide ion. So on this occasion, we've got the lattice enthalpy for magnesium bromide, the enthalpy of hydration for the magnesium 2+ ion, the enthalpy of solution of magnesium bromide. The missing factor is the enthalpy of hydration of the bromide ion. So pause and calculate the enthalpy of hydration for the bromide ion. Come back when you're ready to check against my answer. Okay, so if I reveal the enthalpy cycle, and you'll notice that I've drawn it in the way that OCR Chemistry A A-level questions are generally constructed. That is, I've got the direction of change, magnesium and bromide gaseous ions to form the ionic lattice. I've got the arrow in the direction that matches the definition. You'll notice that we've got 2 bromide ions. So, and this of course will need to be taken into account here, because this value will be for 1 mole of bromide ions. So let's have a quick look at my calculation. I'm saying this is minus 256 and this is minus 2406. So these things added together, those enthalpy changes added together, is going to equal 2 times the enthalpy of hydration of the bromide ion plus the enthalpy of hydration of the magnesium ion, which is minus 1926. So this explains where this equation comes from. Minus 256 minus 2406 equals minus 1926 plus 2 times the enthalpy of hydration of the bromide ion, comes out as minus 368 kilojoules per mole. If you have the OCR endorsed textbook available to you, I would suggest that you now look at page 357 and do questions 1, 2, 3 and 4. Question 3 requires the use of Q equals C delta T, and then check your answers on page 578. So we'll just move on to look at factors that affect the enthalpy of solution, enthalpies of hydration and solubility. So let's consider the factors that affect the enthalpy of hydration values, which of course are all exothermic. That's because attractions are formed between positive ions and the negatively polarized oxygen atom in the water molecule. So oxygen delta minus dipole forms electrostatic attractions and surrounds a central metal ion, which of course is positively charged. Forming attractions is of course exothermic. What would happen to the size of those attractions, the value of the enthalpy of hydration, if the ion was more positive rather than a sodium plus? What about if it was a magnesium 2 plus? Pause and make your prediction. Okay, so my prediction is that the enthalpy of hydration value would become more negative. That is, the attractions between, for instance, a 2 plus ion and the water molecules would be stronger than for a sodium 1 plus ion. If the attractions are stronger with a more positive ion, then the enthalpy of hydration value would be more negative. What would be the effect on the enthalpy of hydration if the ion was smaller? What if instead of a sodium ion we had a lithium ion? Pause and make your prediction. Okay, so I would predict that the enthalpy of hydration value would be more negative. We can think of, with a smaller ion, the water molecules getting closer to the nucleus of the ion. So the electrostatic attractions would be stronger, and therefore the enthalpy of hydration value would be more negative. So let's now consider how changes in the enthalpy of hydration may affect the enthalpy of solution and therefore solubility. We know that the enthalpy of solution is equal to the sum of the enthalpies of hydration of the various ions minus the lattice enthalpy for that ionic lattice. So if the sum of the enthalpies of hydration, which, don't forget, these are all going to be negative, so all of these are going to be negative in value. exceeds the lattice enthalpy value, don't forget the lattice enthalpy is going to be a negative value, then the enthalpy of solution will be negative. So if the sum of the enthalpies of hydration, which of course are all negative, exceeds the value of the lattice enthalpy, or the magnitude of the lattice enthalpy, then the enthalpy of solution is negative, and we assume at this point that the ionic solid will probably dissolve. We will see on the next topic that there is another factor to consider, but an interpretation of a negative enthalpy of solution is that the ionic solid will probably dissolve. So the more negative the enthalpy of hydration values, the more likely the compound is to dissolve. So if the sum of the enthalpies of hydration becomes more negative, then the solid is more likely to dissolve. Conversely, the more negative the lattice enthalpy, that is, the stronger the bonding in the lattice, the less likely dissolving is to occur. So the lattice enthalpy is fairly intuitive. The more negative the lattice enthalpy, that means the more strongly attracted are the two ions within the lattice, so they're much less likely to separate and form free aqueous ions. Not quite so intuitive though is that the more negative the enthalpy of hydration values are, then also, because of its effect on the enthalpy of solution, the more negative these values, then the more likely it is that the enthalpy of solution is negative, then the more likely it is that the ionic lattice will be soluble. So here is a typical problem from OCR Chemistry A exam papers. Predict the relative solubility of sodium chloride and magnesium chloride. Pause and make your comparison with your reasoning. Of course, you should be referring to the fact that the enthalpy of solution is equal to the sum of the enthalpies of hydration minus the enthalpy change for forming the lattice. Pause, come back when you've got an answer. Okay, so my reasoning goes like this. As in this case the cations sodium and magnesium are of similar size, we are not going to consider differences in ion size. However, we will consider the fact that magnesium is a 2+ ion and sodium is a 1+ ion, and therefore the magnesium chloride lattice will have a more negative lattice enthalpy than that for sodium. Now, if the lattice enthalpy is more negative, then that's going to favour magnesium chloride being less soluble than sodium chloride. If this value here, minus the lattice enthalpy, will become, if the lattice enthalpy is more negative, then minus the lattice enthalpy becomes more positive, and that makes the enthalpy of solution more likely to be more positive, and therefore that favours magnesium chloride being less soluble than sodium chloride. We've also got to consider the effect of ion charge on the enthalpies of hydration. So the magnesium being a 2+ ion will have a more negative enthalpy of hydration, that is, the attractions formed between the ion and the water molecules will be stronger than for sodium chloride. So the sum of the enthalpies of hydration will become more negative, and that of course favours magnesium chloride being more soluble than sodium chloride. So this is a favourite type of problem in OCR Chemistry A, where you cannot actually make an authoritative or reasoned prediction. Your answer would be that the effect on lattice enthalpy would imply that magnesium chloride is less soluble than sodium chloride, but the effect on enthalpies of hydration would imply that magnesium chloride would be more soluble than sodium chloride, and therefore you would not be able to make an authoritative prediction. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.